All right. Hello, everyone. Welcome to the Tuesday on Galaxy Evolution Week for KITP Gaseous Halos. I want to, before we start with Crystal Martin's keynote, I want to show a new figure, a new image from Halo 21 Beauty. This is a jellyfish galaxy discovered by Ming Sun, and you can see X-ray emission in blue and purple, and dust lanes, and this is a galaxy, a galaxy interacting with its environment and being stripped. And I think I'm really excited about talking about not just centrals this week, but satellite galaxies as well. So as you can see, we'll be using the Slack channel Halo 21 Week 7 Evolution. So during our keynote today, I highly recommend that you go and use that Slack channel to post your questions, and we will then pick from those as part of our panel conversation afterwards. Before getting to Crystal today, I want to talk about featured conversations this week, and there's a lot of activity. In fact, today we have two after parties. At 10:30 is Halo 21 SCCGM with Nick Battaglia and Daisuke Nagai. And then also Daisuke will be very busy this morning because he'll be doing another after party with Joe Burchett on quenching. So that's 2 solid hours. If you're really into it, I'm going to be there. So it'll be a busy day, but I highly recommend it because these are really well organized featured conversations. And we have a lot of featured conversations next week. And I will talk more about these as the week goes on and build momentum for them. But you can see that there's going to be 4 featured conversations on dust, emission, new instruments, and parametric model, which is something we will talk a lot about. So all of these channels have activity on them. So especially new instruments, which was created yesterday, and also parametric model, and dust and emission have been going on for a while. So I would recommend that you check those out. Before I introduce our speaker, I just want to remind everyone of the social hour coming up on Thursday. And I'll keep on reminding that, and we'll post a link for that as well. Okay, brief introduction today. So now, I believe, is Crystal on? I want to introduce her, Crystal Martin.
I'm here.
Good. I was looking for you. It's a little bit hard with Zoom, but Crystal Martin is our featured keynote speaker today, and she, of course, is a local professor for some of you who are at KITP. She's at UCSB, of course. We assembled a panel. Everyone said yes, so this was our first choice panel. Nicholas Boucher, Xiaowen Chen, Stephanie Ho, and Zach Haffen. So with that, I am going to unshare my screen and allow Crystal to share her screen. Oops, actually, I haven't unshared. Stop share. Okay. Hi, Crystal. Good morning.
Good morning, Ben.
Sure.
Okay.
Go ahead.
I want to start out this morning with a big thank you to our 4 organizers, Mark, Cameron, Ben, and Jess. I don't know, I think the last 6 weeks have just been totally amazing. You have really shown that you can run a super program online, and I hope in some small way I can contribute to that this week. But we all owe you a lot of thanks. Now, on the question you assigned me, that's another matter. This is kind of a difficult question. And if we think back only about a decade ago, now, hang on. We were talking about bathtub models more so than the CGM. And if I was more skilled with Photoshop, I would have a picture of a hot tub here with Avishai and Romil Dave and maybe Nur and Nick Boucher. But this is one of the few pictures of a tub I could find where there was a faucet for the inflowing intergalactic gas and a drain for star formation and outflows. And the small offset between those rates was supposed to be the water level, and in the tub, that was the gas in the ISM. And these models were amazing because they explained so many properties of the galaxy population, but they had no circumgalactic medium. It wasn't deemed necessary at the time. So one thing I want to point out is that in this model, inflows and outflows played a big role, but we didn't really talk about this reservoir of gas that we now call the circumgalactic medium surrounding galaxies. So I think as we go forward this week, it's useful to think a little bit about when the reservoir really matters. Now, with the audience that I have today, you know, if we change the question from do flows affect galaxy evolution, okay, which I'm saying we've agreed on for decades here, to do gaseous halos affect galaxy evolution, we will all raise our hands and answer yes, okay? But again, our challenge is, I think, to be more specific about that and say, you know, Mark Voigt, right, will give us a detailed model, right, about how the precipitation in the CGM is everything, right, and that reservoir really matters. So we can answer a resounding yes. We have a lot of work to do to understand the how exactly, and that's why this program is so exciting. You know, an analogy to take this one step further might be a picture of our local Lake Cachuma at a time of drought. Now, no, this is not the present time, don't worry. But in times of drought, you see, we start to wonder if when the faucet is turned on, anything will come out. And in some ways, maybe that's our circumgalactic medium. Is that reservoir there, and is it full? It may be raining all the time from the intergalactic medium, but if the reservoir is kind of not at a certain level, nothing comes out when we turn the faucet on. So I was trying to think about ways in which the CGM is really essential for our modern picture of galaxy evolution. And I think among the audience out there are probably a very long list we could come up with. You know, two in particular are that I think it's absolutely a crucial part of understanding quenching. And that's not a topic I'm really going to take on today. It's great. We've got the discussion group working on that this week. We'll have a lot of discussion, and I think Greg may talk about it some Thursday. But I think one way in which CGM really does matter is its angular momentum. So now we have spinning bathtubs, right? And that's going to be one of my main messages today, that I really want to argue that angular momentum matters. Okay, so let's step back a minute to the CGM and galaxy evolution. So, I mean, I think several speakers have showed that this plot, we agree that feedback greatly reduces the stellar mass in the universe today, right? The dashed line here kind of shows the mass that galaxies would have in stars if the fair share of baryons in every halo had been converted into stars. And we have pretty strong evidence for star formation driven feedback driving that at one end. And energetically, it makes a lot of sense that AGN are doing the job at the big end, and simulations seem to be able to make that work. So another way, right, in which CGM matters is that besides containing a large reservoir of mass, right, shown here, perhaps a lot of that missing mass that's in the halo, we think they hold a lot of metals. A lot of the gas in the CGM has clearly been processed through the stars in galaxies. And, you know, that's really our thinking behind this whole picture of circulation, and that a lot of these atoms in the CGM have been through galaxies, you know, probably many times, not just once. So another way where I think we start to get to how angular momentum comes into this whole picture about galaxy evolution is when we start talking about galactic disk. And that's going to be one of the things I really want to focus on today. And this is a histogram of gas consumption times, okay, in a sample of very local spiral galaxies. On the top is the molecular and atomic gas added together. The bottom histogram has just the gas kind of in the star-forming part of the disk, which is mainly molecular. And simple calculation of taking the gas mass in that part of the disk, dividing by the star formation rate, shows you that disk use up the gas that's there in just a couple of billion years. And the reason that's important is that that gas consumption time, right, is short compared to the lifetimes of disk. From the ages of stars in the Milky Way disk, we know the history of the disk is much longer than that. And from look-back studies, we know disks have been around a long time. I love this plot from Casey Popovich where he's combined kind of galaxies at different redshifts in candles to make kind of a picture of a look-back time picture of how a Milky Way disk was assembled. And this is today, and you're looking back in time here, and you can see that, you know, somewhere like 10 billion years ago, things that were small disks that look like disk are common and are intact. And then you can see they grow over the next 10 billion years into the galaxies that we see today. So that growth is a really slow assembly. And I think we could argue that the CGM has a lot to do with why that process is so slow. And also, in some sense, you know, if we look back to a few billion years to when the solar system was forming, the fact that our solar system formed, you know, in the outskirts, 8 kiloparsecs away from the center of one of these disks, would not have happened without this CGM that we're so enthusiastic about. Now going back, you know, 10 years or so, again, for the newer folks in the field, you don't appreciate that cosmological simulations didn't have real disk galaxies at that point, that recently. And, you know, it's just amazing what the simulations have done in the last decade. These are zoom-ins mostly within cosmological simulations that form these beautiful disks that we just almost would take for granted today. But getting this to work, you know, it required many things, including resolution. But I think, you know, physically, one of the big things was outflows, driving low angular momentum gas out of the centers of these disks. And then the disk building up over time as the gas that was accreted subsequently had higher and higher angular momentum because it had undergone more torques in the halos. So I just love looking at these pictures of these disks. It's just amazing what all these groups have done. So another thing about disks, though, is that they're big. And not only are they big, their size, it scales incredibly well with kind of a fraction of the virial radius, where kind of the spread in disk sizes in a given size halo is well approximated by just the scatter in spin parameters, okay, that the halos have. So there's kind of a picture here where the size of the disk is a parameter that describes the spin of the halo, okay, that has some distribution times the virial radius. And it just amazes me that besides, you know, late type galaxies falling on this plot, early type galaxies tend to kind of fall on the same relation. So the angular momentum of these disks does seem to be related to the angular momentum of the halo. And understanding exactly how that works, I think, is part of what we're after if we're really going to understand disk. Now, of course, I'm just going to say really two things about quenching, that it happens, right? That star formation does eventually stop in these disks, even though they take a very long time to make their stars. And the most massive galaxies around are all early type galaxies. And that I think, you know, again, COS halos, right, is again really the thing that just turned this field of the CGM on and said there's more to this than just the bathtub model. That the circumgalactic gas is different, okay, in star-forming galaxies than it is in passive galaxies. And because I'm going to talk more about cold gas in halos, specifically magnesium-2 today, you know, I just really want to point out that the cold gas is different in late type galaxies as well. The equivalent widths here of magnesium-2 absorbers are just, you know, significantly higher in the inner parts of the CGM of star-forming galaxies than they are in passive red galaxies. So this is why we think, right, the CGM has a lot to do with how galaxies quench, but there is a bit of a chicken and egg question here of which came first. Okay. So over the last couple of weeks, we've heard a lot of perspectives about how gas reaches the disk, both to sustain star formation and to help disk grow. And my list of references here is far from complete, so I apologize. But there's a picture, right, that kind of emerges here from the simulations where the CGM has high specific angular momentum relative to dark matter halos, a few times higher. And this causes the gas to settle in close to the outer disk. And by and large, these simulations show that gas then being transported radially, okay, at moderate speeds into the inner part of the disk. One of our fearless leaders, Ben Oppenheimer, right, has written a lot about how angular momentum can also contribute to the hot phase of the CGM. And there's new work by Dan Stern talking about an outside-in model of CGM virialization, where he ties the virialization of that inner part of the CGM as kind of a necessary condition for the actual formation of a thin disk. So lots of things we can discuss here later. Another perspective, though, right, we heard comes to this from chemical evolution models, and Filippo was adamant in week 4 that the accretion is vertical. Otherwise, you know, you'd have to flow large amounts of gas into the center of the galaxy, and the speeds required would just be in conflict with observations. So overall, we've got a lot of uncertainty about how this happens, and I'm not going to promise to give you an answer to that in the next half hour here, but I do want to review some things that observations tell us, and I'll bring the simulations in a little bit, mainly as ways to help interpret observations, and most of the theory talks will be on Thursday by Greg. So first, I just wanted to kind of remind ourselves of how gas is distributed in disk. This is star formation rate in the disk galaxy M83 is a function of radius, and these are different gas surface density profiles. Okay, the molecular gas here is traced by CO, and the atomic gas. And the star formation rate, this is a semi-log scale here, you can see is largely exponential in radius, as is the molecular gas density. So just the molecular gas density divided by the star formation rate, because they're both exponential in radius with a similar scale length, okay, gives you basically kind of a constant gas consumption timescale as a function of radius. As you move into outer disk and move into dwarf galaxies where there's more H1, that star formation rate law tends to become more nonlinear with the gas density. And then you end up with gas consumption times that become much longer, okay, in the lower density gas. But if the timescales are similar everywhere to consume the gas you've got, but you've got more gas on the inside to start with, if you're going to stay in some sort of steady state, it seems obvious that the rate at which you need to deposit new gas to stay in that steady state is going to be much higher in the inner parts of the star-forming disk. So I really see where Filippo is coming from here. You need to put a lot of gas and keep it coming into the inner disk if you're going to keep star formation going. Now, it's true in the very centers of a lot of disk, there is kind of a deficit of star formation, but still, there's a big part of that inner disk where we've got to keep stuff going. So this is a bit of a mystery. Now, this is where Yang Zheng's work starts to come in. She did this beautiful study of star clusters in M33, okay, with Hubble, and then was looking, more or less vertically, or had sensitivity via the Doppler shift of absorption lines to vertical motions in the disk. And, saw gas falling down radially onto the disk. I think some of the details of this we haven't talked about enough. And one of the interesting things is that this gas she saw that was redshifted, moving away from us toward the galaxy and falling in basically every sight line, she detected it in the silicon-4 line. Now this is not the hottest gas, right? But this is not what we call the cool CGM either. It was the silicon-4 where it was there in every sight line. And there were other lines of lower ionization, silicon-2, I think phosphorus-2, and some sight lines had them, some didn't. When they were there, I think they matched up kinematically with the silicon-4. But this showed there was some pretty warm gas coming in. The other thing about it is she had to separate, right, the signature of the interstellar gas from this CGM gas that was falling in. And she commented that the non-disk component, the infalling component in M33, it has a rotational component that matches the rotation of the galaxy. So even though we're looking at vertical infall here, okay, the gas is rotating, and even though it's coming in, it may have also been spiraling in from large radii to small. That's not ruled out here. She looked at two models, okay, as the title says here, an accreting layer or just a halo cloud falling in. And because of this rotation component, she said, yeah, this is an accreting layer. The rotation's not consistent with just a halo cloud falling in. And she placed this gas really at a pretty small distance, right, above the disk, just at a half to 2.5 kiloparsecs. So now we're back to our discussions about the ISM interfacing with the CGM. This isn't even really the CGM, okay, by most counts. The rate at which the gas was raining down 3 solar masses per year is enormous compared to the star formation rate in M33, which is largely a big dwarf galaxy. So probably, since this is being detected in metals, this is either fallback from a galactic fountain or fallback of material, pulled out of the galaxy by an interaction with M31. But, you got to wonder, right, if this layer is not connected, right, to these beards that are seen in the H1 21 centimeter maps. So for those of you who aren't familiar with this work, I'm showing here the H1 map on NGC 891 from Tom Osterloh. And these are very deep observations where the outer contour here goes down to something like 10 to the, I think close to 10 to the 17 per square centimeter So very low column density H1. There's this big filament out here. There's probably some sort of infalling material. It seems to be low metallicity based on the absence of dust in this part of the CGM. But it's a really thick layer, several kiloparsecs, many kiloparsecs high everywhere. And if you look at a position velocity diagram projected this way onto the major axis, so we squash the galaxy this way. So as a function of the major axis here, which is what's shown on the right, if we look at the velocity of the gas, well, you see that compared to the rotation curve that's shown by these little white squares and then black crosses, there's a huge range of gas velocities, most of which are subcentrifugal. And this is supposed to be infalling gas. So, you know, folks, here is the infalling gas, right, meeting the disk. And, you know, more recent work by the halo gas group, this paper by Marasco, shows this is actually probably typical, okay, of vigorously star-forming disk today. So this inflow, okay, of speeds, of kind of the rotation speeds here, as you go up away from the plane, that they get slower. They're lagging halos. Speed goes down about, I think, 10 kilometers per second per kiloparsec or something like that. Modeling this, authors estimate inflow speeds of just 20 to 30 kilometers per second, okay, in the vertical direction. Because of the lagging halos, again, it's probably coming in radially as well. So I think, you know, one of the next steps forward, right, is we've really got to work hard on connecting this interface to what we know about the CGM. And I think the simulations are getting close to showing us this. I was really wowed by Dusan's talk last week, where he was starting to show us, hey, folks, this is how the gas actually gets into the disk. Sorry. Quickly here, I just want to point out in NGC 891, there are these really cool observations where they use a single dish radio telescope and they look deep and they measure the H1 gas, okay, out at really large radii above and below the plane, okay, single dish pointings here. This would be dish, not disk, sorry about that, that reach 10 to the 17 per square centimeter. And they're able to make kind of a profile here with height above the plane of the H1 column. Okay, this is shown for NGC 891 in red and another galaxy in green. And these are really neat profiles, I think, of what the neutral gas is doing as a function of radius. They're comparing here to constraints from COS halos that is of, I think this is actually the data on the subset of Lyman limit systems from Prochaska. And there's a large range from COS halos just because that sample, right, spans a large range in galaxy mass and properties. So again, you know, emission is the future, and this is emission actually getting at the neutral gas. Very cool, I think. So now we'll get into the business with rotating halos that has come up and in many contexts over the past 6 weeks. At least from my perspective, this all got kind of started by this 2002 paper that Chuck Steidel led, where it shows you here you've got a galaxy. It's got a rotation curve. One side's coming towards you, and one side's going away from you, and one side's coming toward you. And you go look at a quasar way over here that seems to be, you know, more than a full galaxy's diameter away, and boom, you see a strong absorption system, and its velocity kind of matches up with the velocity of the end of the disk that's close to the quasar sight line. In lower ionization gas, you see it too, and you see it's made up of multiple components. And it's the multiple components that make this structure very broad in velocity space. So these were 5 pairs of quasars and galaxies at redshift of, I think, about 0.6. And it got a whole lot of work started. Now, today, kind of the global picture, that there is, in fact, an azimuthal dependence of magnesium-2 absorption properties, was really driven home by Rangman, Nicholas Boucher, Lynn Capsack's work, and others. I show here a picture from the Lan and Mo paper that's literally combining, like 500,000 galaxies, okay, the sight lines, and showing the difference between, in purple, minor axis sight lines and in green, major axis sight lines, divided here somewhat arbitrarily, okay, at an azimuthal angle of 45 degrees. And you can see that there's a real excess, right? Factors of several here. This is a log scale along the minor axis in the equivalent width. And as pointed out earlier, think of this as the kinematic difference rather than column density difference, because these are pretty high equivalent widths that we're dealing with here. Same thing seen, okay, in iron 2 absorption. Now, measuring these for individual galaxies, when you don't have statistics of 500,000 galaxies, gets tough with Sloan imaging, okay? Here are Sloan R-band images of 3 galaxies at redshift 0.25. Keep in mind, a lot of this work with azimuthal angles is done at redshifts 0.6 and even 1, okay? And this is 0.25, folks. And yes, you can fit elliptical contours to these and measure a position angle and use the axis ratio to estimate the inclination of the disk. And if you have 500,000 galaxies, it's okay, because most of the time you'll get something that's kind of right? It's not a bad approximation. Here's a NERC2 image done with laser guide star adaptive optics at Keck. But in this guy, right, there's these big kind of tidal spiral arms that the real position angle of the disk is here, and the spiral arms move it this way. When you're looking at the Sloan image, it's more tilted. There's an offset here of about 25 degrees. And you also get a much more inclined disk when you actually resolve the disk than you would get from this image that looks like the disk is almost face on. Surprisingly, to me at least, I would say 1 out of 5 times you find there's actually 2 galaxies there, a satellite and a companion, or sometimes 2 physically unrelated galaxies. I'll show later that resolving spiral arms actually lets you determine which side of the disk is flipped toward you. Infrared images aren't great at that, but Hubble images sure are. These are the same galaxies with Hubble. And you can see the disk here and then the little satellite. Very cool. So, I would say we may need a lot more connections to good imaging like this in quasar sightlines if we're really going to connect the galaxy ISM in the CGM. So lots of people are working on this and have been working on this. I'm going to emphasize talking about the work I've been involved with just because I know that best. And this is a sample of 50 pairs of galaxies, kind of Milky Way mass and slightly sub-Milky Way mass and background quasars, okay, where we chose the galaxies first and then took the subsample that had background quasars. And if you just kind of, I should say it's important that these were all galaxies selected, okay, to be viewed at disk inclinations of 45 degrees or higher. So these are inclined galaxies, and that's important here. That lets us line up the major axes of the galaxies. And then when we look at magnesium-2 absorption, well, some sight lines don't show absorption, okay, the X is here. But of the ones that do, it's co-rotating in the same direction as the rotation curve of the galactic disk in all the ones shown in red. And you can see that's the majority of the sight lines that are within about 45, 50 degrees of the major axis. Although some of those sight lines, the gas is really just at systemic velocity, where half of it's co-rotating and half of it's counter-rotating. And you can see it's kind of random if you look at the minor axis, where, of course, if we're looking at a disk in projection here on the minor axis, any circular velocity is tangent to the line of sight, so there is no Doppler shift. The equivalent width of these magnesium-2 absorbers is also important. The really strong systems that are several angstroms, at least in our sample, were concentrated at very small impact parameters and near the major axis. Now, those two things combined really show you are intersecting disk there. Kind of the next category of pretty strong absorbers, kind of 0.3 to 1 angstrom, they really like the minor axis. And the weak absorbers, well, there's no preference, okay? So if you look at weak absorbers, you're not going to find an azimuthal dependence. If you don't have good high-quality imaging, you may not find an azimuthal dependence. And if your galaxies aren't inclined to the line of sight, you're probably not going to find an azimuthal dependence. When you've got good information about the orientation of the disk and the sight line, there's more you can do. And you don't really know ever, okay, as an observer, where that absorbing gas is along the line of sight. So what you do is you get a simple picture in mind and you say, what if? What would the consequences be? And in this case, it's saying, okay, since we know where the thin disk is, let's say the absorbers are there. So what velocity is expected if the magnesium-2 gas we saw was in a thin disk, okay, on a circular orbit? And, well, both minor axis sightlines and major axis sightlines might intersect that disk. Where they intersect the disk would depend on how inclined the disk was to our sightline. So showing that in green, blue, and red here, you can kind of translate this plot into, okay, if we take a disk that's 95 kiloparsecs in radius and it's highly inclined, well, along the major axis, you're sampling it all the way out here, but your minor axis sight line, anything beyond about 15 kiloparsecs, is going to miss that disk. For more face-on disk, okay, inclined 40 degrees, well, you could hit the disk at pretty large impact parameters along the minor axis. So it gets confusing, okay, to interpret such data. So when we have actual information about the inclinations of the disk, though, if we're willing to say what happens if the gas is in a disk, we can deproject back to the disk plane, which is what we're going to do with these data now. And here's where the absorbers lie. Now keep in mind, some of these detections aren't really disk, right? So some were winds along the major axis. We're just projecting back. And you can see that by and large, within a radius of about 80 kiloparsecs plus or minus 10, pretty much everything you see where the sight line intersects the disk plane was in this category of, again, where red is co-rotating gas. And that's why I would say there seems to be some sort of coherent structure. I don't want to call it a disk. I'm going to argue that a thin disk is a horrible description of this, some sort of coherent rotating structure out to at least 80 kiloparsecs. There may be rotation well beyond that that's in more filaments and streams and things. So it makes sense, okay, at least to compare the rotation we see to how a disk rotates. And this is work from Stephanie Ho's 2017 paper, where for about 15 of these galaxies, she's taken the rotation curves and flipped them here so that the side of the galaxy that's near the quasar sight line is at positive velocities, just for show, so they all line up. And if you extend them out to where the quasar impact parameter is, the magenta line shows kind of just the rotation curve extended out where the rotation would be. So the region in yellow is the full range of velocity of the magnesium-2 system. And the green shows kind of the equivalent width weighted velocity. And what you're supposed to take away here is that while the magnesium-2 Doppler shifts always have the same sign pretty much as the rotation curve on the quasar side of the galaxy, if that gas is near the plane of the disk, its circular velocity is not high enough to stay in a circular orbit, the bulk of it. The points here are lower than the magenta points. And if you make another model for the rotation that's based on the halo circular speeds, red squares here, you pretty much come to the same conclusion, okay, that the gas, even though it's got some angular momentum that knows about the angular momentum of the disk, it's all subcentripetal. Now, I think one of the issues that a lot of discussion is going to happen about is how this gas, as it spirals in toward the disk, gets there and what angular momentum transport happens in exchanges with other phases of the CGM or the halo or the disk, etc. But if we just take a simple picture here and say what happens if the angular momentum of this gas is conserved, where would it meet the disk and fall into a circular orbit? You can kind of follow tracks like this. Take this point, and as it falls into smaller radii, it speeds up and it meets the outer disk. Now there's a range of velocities here, so think of this track as a thick line. Sorry about that. As a thick line that kind of meets the disk at a range of radii. Okay. And in some of these, you're coming out and you're adding very much at the edge of the disk. So in this picture, you deposit gas over a range of radii, but it's really biased toward putting gas at the outer disk, unless the gas is losing significant angular momentum as it falls in, which it could be. This is recent work on chemical abundance anomalies that I think really connect to this picture of angular momentum in the halo and gas being deposited at large radii. Okay, these are from a paper by Wang. There's also a more recent one by Liu that looks at the nitrogen to oxygen abundance ratios. Okay, this is work that Tim has been involved in. And using an integral field spectrograph, they've mapped out the oxygen abundance, okay, across galaxies. But then, of course, the oxygen abundance, right, it falls with radius. Well, they've compared to how it should fall with radius, and what they're looking at here is the difference from the expected metallicity. Okay? So, of course, outer disk are more metal poor. That doesn't get you highlighted. It's if you're metal poor or metal rich compared to what's expected at your location in the galaxy. So this should be a symmetric profile, a symmetric histogram about zero change here. And the blue histogram is the data. You can see it's not. It's got this tail toward low metallicity. Sorry, I keep clicking on the figure and advancing the slide. I apologize. So they fit a Gaussian here to the red side and subtract it. And the excess of anomalously low metallicity regions is shown in black. And this gas has some really interesting properties here, okay? If they plot the abundance anomaly as a function of radius from the center of the galaxy, okay, when they're looking at isolated galaxies, you can see that at large radii, there's more of an anomaly. And in close pairs, okay, things that are about to merge, there's more of an anomaly at large radii. And then once the merger's happened and gas is being transported to the center of the galaxy, right, that anomaly moves into the center of the galaxy. So I think they found evidence here, right, that a lot of gas is deposited at large radii and that it's transported inwards, at least in mergers. I'm sure Tim could talk to us more about this. So I want to turn back to Stephanie's work and highlight some of the problems with thin disk and give an example of how she got some estimates of accretion rates, okay? So this means thin disk is not equal to, okay, is not a good description of CGM kinematics. Everyone that's looked at this problem, which is many people over the years, starting with Steidel, have shown that thin disk models are just producing line profiles that are way too narrow compared to what's observed. Okay, so here's a background source. You're over here looking through the disk, and you can see that you will only get absorption over a narrow range of velocities from kind of a maximum here out to these 2 points. So along the line of sight here, the velocity you might see could be represented by this orange curve here, where you can see there's a pretty narrow range of velocities. That range of velocities increases as you thicken the disk, okay, make it thick. And you can play with velocity gradients as a function of height. Those tend to actually require thinner disk than constant rotation with height. And that's the game people play to get broad enough line profiles, is making thick disk here. Keep in mind, though, that even with a thick disk, right, all the projected velocity will be on one side of zero in terms of its Doppler shift, right? It won't cross zero. And many of the absorption profiles do cross zero. So thick disk seem essential, but they can't be the entire answer. There's a lot of work on this, just summarizing some of it here to show some beautiful line profiles. This is the Marasco work in the emission, okay, in the thick disk, making this wing on the 21 centimeter profile. This is UVES data on a redshift 1 disk from Nicolas Boucher, where you see, I think this is magnesium 1 absorption profile here. They've got a model where you see a component coming from the thin disk that's narrow, and then the rest of this is part of their model of the accretion flow coming in there. So in general, accretion flows, they tend to make a broad profile kind of from the velocity of the disk down to zero. This work from Alex Diamond Stanek, okay, where high resolution data, these 3 magnesium 2 components, and along the sight line here, or I like this edge on view through the disk, he's able to connect this strong component, okay, to material associated with a thick disk. The second component in green matches up kinematically with an outflow cone. And then there's this little blue component left over, which is something else, satellite, tidal stream, something like that. So again, the broad stuff is full of components, and they're discrete features, okay, in this cool gas in the CGM. Now, again, returning to what if there's some sort of thickish disk with radial inflow? There's a cool observational effect, okay, that not everybody knows about, that can help you actually test that idea. And it's that if you have a rotation curve, or if you have a galaxy on the sky, and let's say it has trailing spiral arms, so it looks like this, depending on which way the rotation curve goes, whether this side is receding or the opposite side is receding, it affects whether the upper side of the disk is tilted towards you or the lower side. So there's a degeneracy with the tilt of the disk, 4 possibilities here. And if you have both a rotation curve and resolved spiral arms that 95% of the time are trailing, so we'll assume they're always trailing, you can figure out which way the disk is tipped. And when you do that, you can model line profiles, and they give very different results for inflow in a given system, depending on which way the disk is tipped. And Stephanie did this in 3 galaxies, and these are just the results she came up with. In one of them, it was consistent with some radial inflow, got a speed of 30 kilometers per second. Had the disk been tipped the other way, the measurement would have been 140 kilometers per second. That's ruled out. Another one, for her disk tilt, she got 40 kilometers per second. The other solution would have been 80. So, you know, these numbers are remarkably similar to what the simulators are telling us they need in terms of radial inflow. There was another one that I thought was a slam dunk, because in color images, it's really got a blue outer disk, suggestive of recent infall. But in fact, the tip of the disk, it completely ruled out the radial infall model, at least along that particular sight line. So I like this because it can rule things out as well as providing a measurement. So I got a couple slides here on work Stephanie's done trying to observe simulations, again, to get some handle on, okay, what is the morphology of this co-rotating gas really? And here she's looking at a sample of galaxies from Eagle that are matched to her observed galaxies, okay, a little bit less massive than the Milky Way, late type galaxies. And this is a picture of what the cold gas is doing. This is one galaxy viewed, projected on kind of the X, Y, and Z planes of the box. And you can see that no matter how you look at this galaxy, you kind of see co-rotation, okay? It's interesting to ask, though, how much of that co-rotating gas is actually infalling. And through particle tracking, she was able to pick out the particles in red here on the bottom that would become part of the disk on kind of the time scale of one galactic rotation period. And you can see the gas that is accreting is very much feeding the outer edge of the disk. She took that forward in the next step, looked at a larger sample of galaxies and as a function of stellar mass. And here we're kind of binned, okay, into four mass bins. The upper mass bin doesn't have many galaxies in it because she didn't look at passive galaxies too much. The box wasn't big enough. And so let's look at these three bins. And the result was that the magnesium-2 gas was more extended around more massive galaxies, both in an absolute sense and as a fraction of the virial radius. And their flattened structures, the minor axis here did correlate with the net angular momentum vector, okay, of this gas. So here's a picture of, you know, what this thick, disky thing might look like. And there's an interesting observational effect. Here she's considered, if you stack, okay, in this case, you know, 46 of these Eagle galaxies together, and look at a given, we're looking edge on here at an inclination of 90 degrees, look at a given position and say what fraction of sight lines both detect magnesium-2, okay, above some column density threshold, and are co-rotating. Well, that's what the color tells you here. And a color of yellow is the 50% mark, where half the time an observer would find co-rotating gas. So you can see these structures are pretty common to heights of 20 kiloparsecs above the plane, and the red circles are at half the virial radius. You're going to find co-rotation. Well, find is a tricky thing. There is co-rotating gas, but this is gas that was picked out to be inside the virial radius. Picture on the left here. If you project through the whole cube, this is what you actually see, because observers pick out magnesium-2 that's, say, within 500 kilometers per second of the galaxy velocity. But there's significant contamination, Stephanie found, from material outside the virial radius that's falling into the halo and therefore you know, appears closer to the galaxy than it is. And here's a picture on the right of this misassigned gas. Well, in these larger mass galaxies, this is really not a big deal. At an impact parameter of 100 kiloparsecs, the contamination is 5% or something. But as we try to measure this co-rotation in lower mass halos, this contamination is going to be a problem. At 100 kiloparsecs, in this mass bin, the contamination from gas outside the virial radius is 80%. And Stephanie has some nice graphs in her plot that, as an observer, kind of let you estimate at least based on Eagle, what the contamination might be. I really need to be speeding up here. I can see, I just want to advertise the megaflow results from Nick Boucher's group and DeFilippis's recent comparison to the TNG50 simulations. It's really neat how in black here, this is a stacked magnesium to absorption profile that they're comparing to, sorry, from TNG, and then they're comparing to in green the megaflow result. They've really got to pick out the halos shown in red that have the strong magnesium 2 absorbers. They're special, and then they match up pretty well with the observations. But to me, I mean, this is done without any tuning. This is miraculous that the simulations are reproducing the observed velocity widths this well and in kind of a statistical way. And they make a nice comparison in this paper to kind of the specific angular momentum, okay, of their sample here in green, showing that it's likely larger than what in orange the dark matter halos have, and larger than the specific angular momentum of the stars. So take a look at that. I had some things to say on winds, but it's largely recapping a lot of what's been said, so I think maybe I should skip over it and go to the end so we've got time for discussion. I'll make 2 points about it, maybe just looking over my summary, say a few words here. So again, my mantra today has been that angular momentum matters, and it's one of the reasons that the CGM has a big impact, the fact that it's there and it's not just a bathtub on galaxy evolution. We see CGM cool gas rotating. It's not really in a disk in the sense of a thin structure. You could maybe call the inner part of this structure a thick disk. And things look plausible that this is gas that's feeding the outer part of the disk. The chemical abundance anomalies seem to support this idea that there's low metallicity gas being deposited at large radii. To what extent this material can be transported inward in the disk, I think, is an open question. Maybe these thick disks are bringing it in, you know, pretty far, and then it's kind of dropping downwards as it is slowed down by its interaction with the hot phase, so that these flows somehow connect to the picture that Yang Zhang and the H1 beards are showing us. I think this is an exciting direction for future research. The main thing I would have showed you about the outflows that we can come back to if people want to is that they really do imprint a signature on the CGM. Tim Heckman's work has showed this in terms of the carbon-4 and the O6 in terms of cost burst. And in the magnesium-2, the signature is just that the equivalent widths, the velocity spread, is systematically larger in minor axis sightlines of inclined disk than in other sightlines at similar impact parameter. And that shows that either you're seeing an additional component at those sight lines, or you're seeing gas that's stirred up, or some combination of the two. Okay, so going forward, we've got real observational challenges of trying to measure the angular momentum of intermediate and hot gas in the CGM. The simulations are suggesting that those phases have significant angular momentum too, but we've got to measure it. I think emission line imaging of outflows in the CGM is the way of the future. We've got to have a picture. I think there'll be a lot more discussion of that next week. And just to kick off some of the discussion, I mean, I think there are many, many challenges at the interface between theory and observations. I feel like at some level, that's what our program here is all about, figuring out how to address them. And I've already mentioned kind of the mystery of connecting the accreting gas gas directly above the ISM to the CGM. The other thing I would have mentioned in the part about winds is just that, wow, like some of the new theoretical work on launching the outflows, Locas's new analytic model, Evan Schneider's beautiful simulations that really show cold clouds forming out of the hot wind at large distances, and her arguments about the momentum transfer from the hot phase to the cold phase. This is just amazing stuff that's changing our physical picture about outflows. But this begs the question, okay, for this wealth of observational data that are largely absorption line profiles, how does this change how we interpret those profiles, how we extract physical properties about the winds from the data, now that we have a different physical picture of what we're observing? Thank you.
All right. Thank you, Crystal. That was a great overview, and it just shows how much new data has changed our view of what is going on in the CGM, and how simulations in theory have really transformed this field.